and Silva Kumar, Ramco Institute of Technology, Rajapalayam, Tamil Nadu, India, and Medical Engineering College, Sibaraxi, Tamil Nadu, India. So please start, maybe Jay Javins.
Yes, sir.
Jebin, share your screen.
Wait a minute, sir. Sir, can you please, I can see that host disabled attention screen sharing. Can you please make me the hello?
Yeah, you can share now. Oh, I come.
You have to make me host, I can say, sir. Host or co-host.
Yeah, I think you can.
Okay. Whether my screen is visible, sir?
Yes, you can start. You can make full screen and start.
Okay, so good afternoon to everyone. Myself, Jabin, assistant professor from Ramco Institute of Technology. So as part of my research work, I have did some
Can you make it full screen?
So now I have made it to full screen.
Not yet.
What about now, sir?
Not yet.
Wait a minute, sir. I will stop share and again I will start share. Can you see my full screen, sir, now?
You have to make full screen option, right?
What about now, sir?
Not yet. Okay, so it is you have to make
can you please tell what you are seeing in my screen, sir?
no, just without full screen, I can see only PPT. Okay.
Yes, sir. My actually I don't have a video device, sir. That's why.
Not video. You have to make full screen. No, that.
I have
Presentation
used
mode.
Shift. Yes, sir. I have used Shift F5, and now it is in full screen mode in my system.
Oh, in your system.
Yes.
Okay. You can go ahead. Okay. So
yes.
You don't want to waste it.
So good afternoon to everyone. So my research topic today is experimental investigation of mechanical and wear behavior of copper vanadium graphene composites. So far I have completed 2 research papers. So based upon in this area of research. So basically the thing is copper is having a good electrical and thermal conductivity, as we all know. But the main thing why copper lacks its application is because due to its poor mechanical properties, its low hardness. Okay, so those things narrows its application. So based on this problem identification, I thought of strengthening the copper so that it can be used in many areas. So based on that, I have collected some literatures. So what are the things which researchers have done with the help of by in this copper field. So based on that, I have collected some literature. So I'm not going deep into all of those things. So these are all the literatures. Many researchers have used different kind of reinforcements to enhance the properties of.
Excuse me, it's not moving. Your slide is not moving. No,
Um,
we can see only your first slide.
Hello, sir. Hello.
Hello, sir. Hello,
Yeah, yeah, yeah.
Sir,
No,
sir.
we
I
it is
have just
a cup button, cup symbol. You have to click on that for full screen. And volume place and system.
yeah, yeah. Can actually you have uh first option. You have to click on the fourth option. Near to the volume, right? Near to the volume, plus minus, right?
Yes,
So
sir.
near to that cup symbol. Can you please click on that? Otherwise, we can't see anything.
no, sir. Where is it, sir? I
No, in the
just can
bottom,
see.
in the bottom actually, in the bottom of your screen, right side, near to plus minus symbol, right? The volume control.
No, sir. Actually, I have joined using browser, sir. It is not the application.
Whether it is
So what?
PPT or not, it
It
is
is it is it
PowerPoint
is
fine.
PPT only, sir. PowerPoint, sir. PowerPoint only.
Okay, then you can make it full screen, right? Actually, we can see that cup symbol. You have to click it. Okay. No, in your screen we are watching. No, the right side bottom there is a cup symbol, right? Near to the textbook symbol. After that cup symbol, right?
No, sir. I can see more option record chat box, sir.
No, I am asking in your PPT. No, in your
Yes, in
PPT.
my PPT, yes, sir. Yes, sir. This is my PPT. Now you can see it is not in the full screen mode. Now I am just clicking on that cup symbol. Okay, there
Okay.
it is named as slideshow. When I click on that, it is becoming big. But I
Yes.
think you are not able to see my full screen. I don't know what is the problem. I'm familiar with this all kind of tools. There is no issue in my side. I don't
Okay.
know what is the problem in that side. How why it is not visible to you all, not visible to you.
Now I think it's already 4 minutes past. We can't see. We can see only your
First
first
slide.
slide.
Okay, sir. Wait a minute, sir. I will log in. Within a minute, I will log in by using my other system.
Yes.
I think
Sensei.
Finish is back.
Yes, Sensei. I think he will rejoin. Yeah, Vignesh is back, but his time is gone, Sensei.
Okay.
So he didn't join on time. So now, as per the schedule, we have to go. It is not a real time event because the next will affect. It's in I think we can allow him, Sensei. So Vignesh, if he joins, so we can allow him another 10 minutes only. We can allow him. So
Okay.
can we?
So maybe we go to the last presentation.
Sir, you please proceed, sir. I will present my research at last, sir. If you give 5 minutes, means I can present at last. I will switch over to another system so that it may be.
Okay, okay.
Okay.
So se- can we allow Vignesh Sensei?
Mhm.
Vignesh, are you there?
Vignesh?
Hello, sir. Good evening, sir.
Yeah,
Good
you
evening,
can
sir.
share your screen. Yeah. You can.
Yeah, yes, sir.
Yeah.
Sure. But it seems it is disabled, sir. Sir, uh, the I'm getting host disabled participant screen sharing, I think.
So now you can try.
Yeah. Yes.
Can you make it
Actually,
full
Can
screen?
you can you see my screen, sir?
yeah, we can see, but maybe you can go to the full screen mode.
Yeah, yes, sir. Yeah.
Yes.
Okay.
Now it is okay, sir.
Yeah.
Yeah, but
Yes, sir.
actually we don't have enough time. So maybe you
Yeah,
can
yes, sir.
present
Sure,
quickly.
sure, sure.
Yeah.
Yeah, yes, sir. So, good evening, one and all. I'm very happy to share my research ideas on exciton Moore transition in asymmetric double quantum well. I have used Thomas Fermi dielectric screening for this study. So this is the short introduction about excitons. So I'm skipping that for time being. So this is the idea. With this, I have started. So whenever laser light is incident on some semiconducting material, the optically excitons will be pumped when it is in cryogenic temperature means. So at some peculiar situation, that means that at some critical concentration, these excitons will break into electron hole pairs. So depending upon the exciton's density as well as their temperature, we are going to get different kind of exciton species like exciton gas. When you come to the lower concentration, exciton bosons in condensation will take place. When you go to a higher concentration, exciton electron hole BCS state will be formed. So I'm going to study this exciton Mann transition in between these regions. So this is the experimental idea. Recently studied in one paper. So it shows that in a biased asymmetric double quantum wells, you can form both direct as well as indirect excitons, so that at some particular situation, these indirect excitons will stimulate. That means it is going to transfer one of electrons into next quantum well, so that trions will be formed. So this will lead to exciton Moore transition in nanostructures. So this is the experimental idea we have seen in this. So we want to study a theoretical model for this. So with these questions we have started. Is it possible to derive a simple theoretical model for exciton Moore transition in quantum wells? And then if it is the case, what will be its nature? Because still it is a puzzling phenomena. That means we don't know, people don't know whether it is a first order transition or second order transition. So such a question is arising. Third one is, if it is possible, if it is possible in double quantum wells also, because in double quantum wells you will be getting direct as well as indirect excitons as shown in the experimental work. So we already studied this exciton Moore transition in single quantum well as well as symmetric double quantum wells, and we published these papers in AAP conference proceedings as well as Physica E low dimensional structures, and we got that this particular exciton Moore transition in double quantum well will be showing an abrupt change in the diamantic susceptibility that characterizes this particular exciton Moore transition will be of second order. Okay, so I want to study that in asymmetric double quantum wells. So this is the theoretical idea I have used. I'm going to use variation technique for studying this. I am going to use Thomas Fermi dielectric constant for screening mechanism. That's all. So this is the result I've obtained. As you increase the exciton density, that means in the x-axis, it shows exciton density in per centimeter squared. First, I have studied binding energy by varying different asymmetry parameters. So in all the cases, what I observed is I can get exciton Moore transition at some particular critical concentrations. So before that, so as you increase, if you see that as you increase the exciton density until 10 to the power 13, the binding energy of those excitons will be stable inside the double quantum well. Immediately after that, gradual decrease in binding energy will happen, and then it will vanish. So this shows exciton bond transition is taking place in asymmetric double quantum well also. I have studied in 2 different quantum wells. That means coupled asymmetric double quantum wells. That means at the central part, I have fixed central barrier as 50 angstrom unit, so that the coupling will be very strong in the asymmetric double quantum wells. In the second case, it is decoupled quantum wells. That means I've set a bulk limit for the central barrier, so that there will not be any communication between these 2 quantum wells, so that I can able to study both the cases. In all the cases, I have observed this exciton bond transition. When I study about diamantic susceptibility for excitons, it is I have utilized spatial separation between electron and the hole pair. So I have used diamantic susceptibility for this particular study. Here also, I can able to see that Mach transition is taking place with the abrupt in nature. Okay, so whenever I increase direct exciton as well as indirect excitons concentration, it is showing an abrupt change in the diamantic susceptibility. So in the earlier case, it is gradual change. Here it is abrupt change. So that based on this, I can able to suggest that this particular exciton bond transition can have second order nature in nanostructures. So this is the critical concentrations I have observed for LB equal to 50 angstrom. That means strongly coupled asymmetric double quantum wells. As you change the asymmetric parameter like 0.5, 1, 2, 3, 4, so you can get different critical concentration for the Mach transition.
Vignesh, you have 2 more minutes.
Yes, sir. So if you see that in wider quantum well, that means there is no tunnel coupling at all. So in that case also, it is executing. It is showing exciton Mach transition, but with a different carrier concentration. The same I have done and observed that for indirect exciton case also. So it is also showing exciton Mach transition in asymmetric double quantum wells. So this is the conclusion I have arrived. Exciton Mach transition so we have theoretically studied using Thomas Fermi dielectric screening combined with variational Monte Carlo techniques. Okay, so the exciton Mach transition is observed in both coupled as well as decoupled asymmetric double quantum wells, and for direct as well as indirect exciton also we have studied this, and it is showing that chi-dia is changing abruptly at when you come to the critical concentration. So in nanostructures, this critical concentration is going to change based on the well dimension, barrier dimension, and the type of excitons and their nature. Okay, so this study can afford a greater support to the time-hollowed argument of exciton Mach transition's nature. Thank you.
Thank you, Vignesh. And maybe we don't have time, so maybe we can take just one question.
Yes, sir.
Are there any questions?
Participants, if you have any questions, so kindly raise your hand or put it in chat box, so we will check it for you.
Okay, so maybe if you have any questions, we can put in chat box, and we go to the next presentation. Is it okay?
Yes.
Okay, so thank you, Vignesh.
Thank you, sir. Thank you, sir. Thank you.
Okay, so we move to the last presentation, CL3. It's the investigation of microstructural, mechanical, and tribological properties of aluminum 8011 TSC metal matrix composite, Langnas, Paranikami, Jakuma, Lux Himpathy, Alna Engineering College, Tiruvannamalai, Tamil Nadu, India. So please start.
Alanisami, are you there? Alanisami Raghunathan, right? Raghunath Palanisami, are you available? Raghunath Palanisami?
Hello.
Oh,
Yeah,
he's there.
yeah.
Sir, can you hear me?
Yes, you can share your screen.
Okay, sir. Sir, can you change the settings for me, sir?
Yeah, yeah. Now you can do that.
Sir, can you able to see my PPT?
Yeah, make it full screen.
Now, sir?
Yes.
Oh, thank you.
Okay.
Good afternoon to everyone. My research is about investigation of the aluminum series. Particularly, I have selected an 8 series, which is a currently newer one. What I done is that with the composite materials, I have added various elements, but this is one of the part which I added a little amount of composites to the aluminum as a base material. Okay. Why aluminum is ideal one? Because aluminum is very suitable and it is has a ability to satisfy the what required and what demands it has from the now the engineering application has. Okay. And along with the composites, that means additional materials, aluminum has the ability to enhance or improve their basic properties like mechanical or tribological properties. It can enhance it with addition of the composite particles. And apart from that, aluminum is a very ideal one with the low density and high strength properties. Basically, aluminum, why it has been chosen means due to this one. Apart from that, when you are into the mechanical properties, it has a good wear resistance property, better corrosions, and thermal efficiency comparing other materials. It has a very low one. And lastly, when the comparing 10 to 15 years, you can see that usage of the aluminum is being maximized because of the um, better exhibiting the mechanical properties. Okay. Here I have chosen as a aluminum matrix composite. From that, mainly I have chosen as a titanium carbide as a additional material, and titanium carbide has been blended with a base material, monolithic material aluminum with the various ratios. Why various ratios has been taken means how it differs from comparing the monolithic material, how it has been how it exhibits with the titanium carbide, and what are the properties it exhibits, and for different ratios how it behaves, we are all analyzed. Okay. This is a full research I have taken out. As a composite material, monolithic I have taken as aluminum. In that aluminum 80W1. As a composite materials, I have taken TAC, SIC, B4C. But this presentation is all about only TAC. My further research has been included with silicon carbides, boron carbide. Everything has been included to make sure that in order to make sure that we have a very strong possessed material, which is very suitable for nowadays any automobile or aerospace industries we have to give. So experimental setup has been done with the casting. From the casting, I have used as a stir casting method because it is very conventional one and easy one. We can easily, it is available in a every area. Machining further part is when used lathe and so on. So there are various machining process and other cuttings, grinding, everything has been done to in order to make that tensile specimens, impact specimens, hardness specimens. We are pinout disc, everything has been done. So mainly the analysis is all about a tensile wear, impact hardness, and a microstructure. Along with that, SIM has been carried out to ensure that how the wear rate and how everything has been placed. Okay, microstructure has been done on trianomacular microscope, and my combination is all about a 5%, 7%, 9% of TAC with aluminum monolithic material. Okay, why particularly I have stopped at a 9 means that you will see it because if you see in the first image is a if you see in the first image it is a 5%. You can see the closely bonded particles, and when 7% it is okay, but when you're into the 9% means it is a various porosities and various cracks has been formed, because whenever the titanium carbide is been increased, okay, beyond the 7%, beyond the 7% it has been increased means what happens means due to the heavy particles it take down all the aluminums and everything, so there is no correct bonding has been done, and it makes a more residual particles deposited under them. Okay, so there is no correct blended has been happened when you are increasing the titanium carbide beyond 9 or 10. If you are going beyond the 9, because of the due to heavy metal particles, it heavy properties possessed by the titanium carbide, it makes a more slag, so there is cracks and other things has been formed. Similarly, when you are into the hardness, if you are into the 9% means the hardness has been decreased because there is no proper further adding of the titanium particles and no correct blending with the aluminum. So what happens now when you are seeing as a aluminum, you can see the gradual increasing when you are adding a titanium carbide. Okay, but after that 7%, you can see that projection has been going down. This is mainly due to the improper bonding with the aluminum, and maximum slag formation has been formed. Okay. Similar to the tensile strength, you can see that we have taken as ultimate strength and yield strength with the calculation we have done. So it is similarly, if you are into the like hardness, that same projection has been done here. When it is on above maximum, it has been done maximum value. You can get it on 7%. Further
Raghunath,
yes sir,
you
yes
have
sir.
2 more minutes.
Okay sir. Okay. Further, it has been decreased. Similar to the impact test, you can see the maximum hardness value on a 7%. Then the impact value has been replicated. Similarly, wear test for coefficient of friction, you can see that very different loads. When the load has been increased, the coefficient friction has been reduced systematically, but whenever it has been reduced means, but it shows that at 7% you have the maximum value when you are comparing into the all loads. Similarly, for the wear loss also, you can have the minimized wear loss when you're into the 7%. By comparing the load, whenever the minimum load has been done, the wear loss has been decreased. Further, same analysis has been taken. The A is replicated the aluminum 80, B, C, D are with the percentage 5, 7, and 9. You can see that C, there is a clear indication that there is no oxides or there is no flux, anything, nothing has been done. It has been minimized when comparing to the other things. This is the XRD pattern. I have taken it to confirm that TAC particles presence in a aluminum, as well as EDS has been taken out to ensure that TAC particle has been done. Similarly, these images is being done for a 20 Newton maximum load. For maximum load, it has been taken this same analysis. What I am concluded is XRD exhibits that existence of T is in the matrix, and similarly for hardness, impact, and other wear resistance, it shows that 7% exhibits a higher values, and the amount of percentage has been denoted 35 and 170 and 150 respectively for a micro hardness, tensile, and yield strength. From that, I am concluding that beyond the 7 or 9%, if you are going with the aluminum 8011 as a monolithic material, it keep on decreasing. I have done it at 10 or 12, I have done it, but it is drastically reducing because of the due to the heavy content it possesses, TAC. It mixing a more slag formation. Okay, sir. Thank you, sir.
Thank you, Agnes. Now paper is open. Are there any questions and comments?
I think no
Okay, maybe
sense.
I have one question,
Yes, sir.
and maybe your composite with TIC of 7% composite
Yes, sir.
has a very good result, maybe. So do you have any reason for that?
Sir, in a 7% TAC, it makes a better combination with the aluminum, sir. Even though 5% is also having a better combination with aluminum, but the result, the presence of titanium is less with the percentage. The 5% is been taken with the aluminum value, sir. For per kg or 2 kg, it has been taken on the percentage like that. But the presence of TAC 5% is exhibiting a lesser mechanical strength value. But if I'm increasing on 7, 9, 10, it goes on like that means everyone says that keep on increasing means it will exhibit the good properties. But when I goes on 9, 12, 15, it goes on like that means what happens means that TS is a very TS is a very optimal.
Raghunath? Raghunath? So connection.
Okay, so maybe I think we have no time.
Yeah.
So maybe it's good to close the session. But before that, I'd like to express our appreciation for all speakers for the very good presentation and also audience for the very nice discussion. Thank you very much for all.
Thank you, sir.
So maybe it's time to close the session. Thank you.
Okay. Thank you, Yamada Sensei. Yamada Sensei,
Hi.
thank you so much.
Thank you very much, Yamada Sensei.
ありがとうございます。And
ありがとうございます。
I will attend the student interaction tomorrow.
Yes, Sensei. Yes, Sensei. Yes, Sensei.
Are you going to attend that event also?
Yeah, I will attend, Sensei. So to watch your talk, so how you interacting with this school children. So when I was a JSPS student, there we done, school